So before going to discuss about the visual MODFLOW, I'd like to give an overview on MODFLOW software. So yeah, these are the different softwares available for groundwater flow modeling: MODFLOW, WebFlow, Plaxis, ArcHydro, HydroGeosphere, and all. So among these softwares, I'm gonna show MODFLOW software. So MODFLOW is a modular finite difference flow model, which is developed by USGS. So these are written by it was written in Fortran language. So these are the different versions available for the groundwater flow modeling in MODFLOW. So coming to Visual MODFLOW is available in 2D and 3D. So 2D, we're gonna see the 2D version. So Visual MODFLOW, it is like it is designed to model the groundwater flow model, and it was developed by Waterloo Hydrology company. So uh, so these are different solvers available in Visual MODFLOW. Solvers has like its importance in modeling in getting the output. So in some conditions, some solvers won't allow us to, like, they will try they will cause an error. So in certain situations uh, we could use in those situations we could use the other solver. So here we can see like WHS solver, which is like which if no other program run without any error, like if you got any error in any other solvers, most probably WHS solver would help us in running a model. And yeah, in the Visual MODFLOW, these are the simulations available for the mode flow, mode path, zone budget. Zone budget has it's like it will give the total input to the aquifer or region or whatever county. So amount of water into the surface or aquifer, and amount of water went outside from there. So it will give kind of budgeting, water budgeting. And yeah, the graphical visual interface is the uniqueness of Visual MODFLOW, like good graphical visual interface. I don't say it's in, yeah. So coming to the software, so who who so this is a Visual MODFLOW window. So we need to open the if we have any existing files to edit or do we can open the existing file. So right now I'll try to create a new file and just view an overview on the Visual MODFLOW. Then I'll try to go back to the existing file and I'll show you the outputs and all. So we need to click file, then go to new. Then we need to create a folder or file. Like I'd like to say, yeah. So the file name is that. So suppose like let's take, so we are gonna study the groundwater flow in the Fargo Dome, under the Fargo Dome. So let's assume so to recreate the conditions. So first we need to know the latitude and longitude, or length of the Fargo Dome. So first suppose its length is like somewhere around 1,000 meters. So if we have base map, we are gonna we can directly click check it, and we can browse the base map to get back into the to work on the map. Base map is like so suppose in our example we said like Fargo. So we can get the base map by, so go to Google Maps. We can zoom out, like completely zoom in, such that Fargo Dome should sit to all the frame. So the four quarters of the Fargo Dome should be there, and using snipping tool or any other sniping tool or other tools, like just crop the Fargo dome and just convert into BMP. Those formats are in JPG or PNG or JPEG formats. It won't take, Visual MODFLOW won't take those formats. So we need to convert into BMP format, which is like basemap format. I'm sorry. So we can convert that. We can do using Google or online conversion. Be okay for it. So after converting the base map, we need to we need to we also like if you want to work on the latitude and longitude, or you need to note down the four corners, latitude and longitude of four corners of the uh, boundaries of the base map, or else we can measure the length for length width of the Fargodom or our location. So yeah. So if we don't have base map now, so I'll directly click the give the dimensions later. So number of this is the columns. So after inputting the base map, we are gonna have like we're gonna divide the whole area into small grids. So suppose this is a small area. I'm gonna do small grid. So it has certain impact. For large areas, we need to take more number of grids. So we're gonna decide. So for this example, we'll say some 50 by 50 grids. So 50 by 50 grids, it means whatever the dimensions of the map, irrespective of dimensions, we are gonna get only 50 grids on the study area, whatever it is, how much it is, like we'll get 50. So then this is the minimum and maximum. It is the elevation. So to model the groundwater, first we are going to give the surface elevation. Then we will be having our soil will be in different layers. So we are going to layer them. We're going to give layers in input. So to say that, suppose if we have clay soil at till 20 centimeter deep, 20 meters deep. In this case, from the mean sea level, we have to give the elevation of the Fargo dome, elevation at the location, and bottom is 20. So we need to give X max and X minimum there. Similarly, yeah. Then how many layers we are having? So suppose in some study areas, we are going to have like more than 2 3 layers, like uh, top layer, though suppose in some areas like sandy layer is a little like some 3 4 meter deep, followed by clay soil divided, followed by some granite gneisses or some hard rocks and all. So we're gonna have 4 5 6 7 8 layers. So in these cases, like we are gonna tell the model that in our study we are going to create some 6 7 8 models. For example, in this case, like we'll say we have 2 layers. Then Z minimum, Z max. It is like yeah, it is a thickness of the layer, and x minimum x max is the dimension. I mean, my apologies. Yeah. Okay, yeah. So x minimum is the if suppose this is the Fargo. Suppose yeah, this is the Fargo dome. So this is the length, this is the width, right? So x and y axis, where we going to give it is 10 centimeter. It is 10 meters, sorry, 1,000 meter, and this is 2,000 meters. Means we're going to give, we're going to give, it starts 0, 0, 10, 15, 20, 30, like 1,000. 0 again, 0, 10, 20, 30, 10,000. So it depends on we are going to give some readings, like the length of the field, width of the field, it based on. So when if we are going to use the latitude and longitude, we're going to give the latitude, longitude, the minimum latitude, minimum value, and the maximum value. That's how we're going to. So suppose in our case, let's say some 30 meters deep, and yeah. It's frozen. Then that's all. So our model is almost ready. If it is a transport model to study the leakage and all, leakage of the flow and all, like any leakage in the any spillways, some in those case we can use the transport model. Now we are just going to discuss about groundwater flow modeling. Just click the create. That's all. We got our model with all grids. So you can see x minimum is 0 and it went to 1000. Y minimum is 0 and we entered it as 1000 because we assumed that our study area is like 1000 meters deep, 1000 meters. I forgot to show you that. Like after creating the model, we got an option to choose the units in meters or feet, whatever it is. So yeah, we can use that too. So then, so this is our top view. I mean, if this is the Fargo Dome, this is the base, and this is the top of the Fargo Dome. So when we see from the top, satellite view, Google Maps, you can see the top face, the face of the head of the Fargo Dome. So this is one. This is the one. So we're gonna slowly, step by step, we're going to give X, Y, like first we are going to give the layer thickness and all. Then we are going to locate observation wells or piezometers, whatever locations at different locations, and followed by other properties. So now we created the model. We created the model. We need to give the thickness, the layer elevation. To do that, we need to import the elevation. Import the elevation could be like we can save in XYZ, or Surfer is a software. I hope you guys are aware of it, which where we could get the XYZ. So in this case, we are going to give the first one. I mean from ACXYZ, right? So how so after getting, if we know the surface elevation at different locations, suppose we have 1000 meters, 1000 by 1000. So randomly at different locations, we need to get the uh, surface elevation of the study area. Now we will be saving x as x direction, length, and y direction. Suppose to give the elevation here, we need to say 200 comma 0 comma elevation. Suppose the elevation at 200 location is 20, then we'll say 0 200 20, which means 0 is the, sorry, 200 0 20, which is x coordinate is 200, which means length, then y coordinate is 0 and 20 meters. At this location, the surface elevation is 20 meters. Similarly, we need to give it randomly as much as possible. If we have more numbers, the more accurate data we'll be having. The reason behind this is, so after doing that, we will say this is the ground surface. When we are going to give the ground surface, we have to click it. After giving the ground surface, we are going to give the elevation or thickness of the next three surfaces, like soil surface, sandy soil, clay soil, or other soils. So to give the thickness, we need to say import, click the import bottom elevation, then click which layer elevation are we going to incorporate. Then we would say the layer thickness. It's kind of like how much thickness you want to see the layer. That's all. Then so after giving that, suppose if we have only two three values, it will definitely take it, but we will fail to recreate the real conditions, because if we give some two locations, it is going to do the interpolation and it will give same value for each grid. So suppose if we give 20 and 40 here, it will do interpolation and it will do. If we give 1000 values, it would take. So that's how it works. As many points, it's better to recreate the location. Now we need to check whether our data is correct or not. So to do that, just click, like don't need to click, just go to the any known coordinates and just place the cursor there. We can see XYZ here. X is the X location 16.6, Y location, and Z is 22.5, which is like we didn't do anything. So that is how it's showing 22.5 everywhere. So that is how it works. 22 point. So slowly we need to import the other layers. Then so after importing things, we can view them. I'll show in the existing file later how to view and all. So then we're gonna click some pumping wells, just save it. Like, properties like we have. I think it's better to in the existing file so that I can show you better. So I'm gonna open the existing file. This is one of the existing file, like which this is a base map actually. I just yeah. Sorry. So yeah, so this is the base map. So I would like to delineate my study area. So I used inactivate cells. So we have mark single. So if we mark it, those cells will get inactivated. So that is how I delineated. Suppose if this is the Fowler dome, I'm gonna delineate this. So this is my study area. I'm gonna work here. This is like excess portion, so I don't want to use them. So that is how we delineate them. Then you can see how the XYZ is changing. You can see the elevations here, how Z, how it is changing, 3.8, 9.4, which has high elevation. So then we are going to, after importing the elevation, and after delineating, we'll import the elevation. After importing the elevation, we are gonna give the pumping well data. We need to save it because I don't want to save it because after running the model, it may cause error because we have many observation wells here. So for to let you know, I just did that. I didn't save that. So, yeah. So to add the pumping wells, we'd say this is a in my study area there is a pumping well which uplift the water from one river and will around it will discharge everything in another river. So I just addressed a pumping just click add well, whatever it is based on the location. We know the location, so based on the location, just give the well name, then coordinates because we can see the coordinates here, this XYZ. So I will get the coordinates. If you want to move the well, then give the existing coordinates, correct coordinates of the well, then screen bottom. So while giving the observation wells and pumping wells data, we're gonna give, so it will ask the well screen. And so usually, suppose the mean sea level is it's 0, right? So if you wanna give the top from the top, I mean the depth, groundwater depth, we need to choose it. We need to give the groundwater depth from the surface of the surface. That is how it will take. So we need to give them in from the surface, or this is the elevation. It takes from the elevation. It is depth, which means we are going to give with respect to the mean sea level. If you want to give the water depth with respect to mean sea level or surface, based on that, we can check it, this elevation and depth. Then we're going to give starting day. Suppose in day one, it is 0 to day one, and how much rate it took. Then 1 to 10 days, how much it took. So suppose like this. So in 10th, from 10th day to 650 days, how much it. So that is how we're gonna give the pumping rate. So usually we'll be having some pumping wells or observe pumping wells or other drainage and all. I mean drainage canals, we are gonna give them as boundary conditions. So yeah, there is any pumping well in our study location, we're gonna get it. So Next, click next. It is in the second layer. It is in the third layer. Like so, my study area is has around I guess 10 layers. So I am having 10 layers. So if you click next, it will take to the next layer, third layer, fourth layer. This is the seventh layer. This is the eighth layer. You can see here. This is the number of layers. That is how it will do. Then properties like wells, head observation wells. We are going to address head observation wells. So in my study area, we are having somewhere around 51 observation wells. So just like add observation well the same way, we're gonna name it, give xy coordinates, observation point. It will take automatically. So time, how many days? So first 365 days. This is the head observation well head is 9 meters, 6 meters deep. Then from 600 next some 698 365 to 698 days it went up. Other days it went down. So that is how we are going to give, and we'll click OK. Then it will take the observation well readings. So for example, I'll show you the readings in my study area. So it says that the Pragadavaram, which is the name of the village, and its XY location is its location. And this is the in first 62 days, its head is 108.9 meters. In 121 days, it's almost like 83. It went down, down, down. It's going down. It increased again. So I mean, it's deep. It's going down. It is 108 meters from the top. Then it went 109 meters, 110 meters, 112 meters deep, 117 meters deep. It's going down. That's what it's showing. It's saying that it is from the elevation. That is why it is from the elevation. So after assigning the observation wells, we need to say concentration observation wells. This is for transport models. If we want to address some spills and all, we're gonna use that model. So then this is the main part of the study. We need to address some properties like hydrological properties. So conductivity. So we can assign the hydraulic conductivity in layer wise, polygon, or whole window, or single. Single means we need to click somewhere and it will say how much. We need to give the hydraulic conductivity. For to assign the polygon, we need to click select some layer and we'd say in this location, because though in some very big area, suppose if we're gonna do for Fargo, whole Fargo, soil, if suppose half side is like some other soil, half side is Fargo clay soil. In this case, we're going to give Fargo clay soil one hydraulic conductivity, the second layer as second hydraulic. That is how it works. That is why we need to use the polygon. And then uh, storage, how much water storage and all, like I'm sorry, that's not storage capacity and all. If this we're not going to give that initial heads. So after giving the so this is completely based on our well observation data. So we gave the head observations, right? So based on head observations, this made this graph. I mean, it's not like it gave the head observations for each location. Each color represents single value. So that is how it shows. So it made the initial groundwater flow condition for the model, followed by initial heads of this. These belongs to transport models. So now we created the soil surface. We created the surface, our location of the study area. We gave the elevation. We gave the layer thickness. Then we gave the pumping well data. Then we gave the height observation well data. Then we're gonna address the boundary conditions, which is very important now. So boundary conditions, they will help us to understand, to study the uh, so boundary conditions means any river drainage canal or rivers, drainage canals, rivers, seas, or any water surface bodies. So these all comes under boundary conditions. So in this study, so my study area is located in a, I think I can explain it here. So yeah, got it. So in my study area, so if it is my study area, this is Bay of Bengal Sea. We have sea here. We have a river Godavari river, river A here, and we have another river here, river 2. So this is my study area, and it has a biggest longest lake, like good water, like pure water lake. Then this is the study area condition in the model. So I'm gonna address that. So usually, coming back to the same. So I gave the red color represents the sea location, Bay of Bengal, and I gave it as, if you go and see there, I said its head is 0 because it is sea. It has it is 0. Obviously, it is 0. Its head is 0. Then I assign a this is constant head, which means C. Constant head, which doesn't change. We need a constant head. So that is what I made here. If we don't have constant head, we would say some any water existing water body which won't change for a while. So we could say we could address it as constant head. Then coming to the rivers, this blue layer shows the blue river section. So I gave it. So from starting day, in first stage 0, in the second stage 365, the river stage elevation at that location, and this is the river stage bottom, and so to give the to recreate the river location, we need these values. We need these values to recreate the model. So I allocated assigned the river such a way that, suppose, like this I arranged. I mean, based on the XY coordinates, I followed and I assigned a river and I right clicked it. It means my river layer, I allocated the river layer. So I need to say how many days? 365 days. What is the river elevation at first location and the river elevation at the bottom location and its conductance. Conductance, there is a formula to calculate the conductance. So we have to calculate the conductance and I assign the conductance. If suppose, then I click enter to assign because it's not, I have 5-6 years data. Suppose if I have 7-8 years data, I would say for first year how much it is, second year. If I don't have year-wise data, if I have together 7 years data, then I'm gonna give like 7 year, how many days for 7 years. I'll assign some days there. That is how we can assign the after reverse. I assign some drawing. This cement color or whatever it is, I guess cement. Yeah, gray color. Yeah, yes. So this presents the drainage, the drain canals. There are like few drainage canals over there. So I just send them. This directly drains to the sea. So yeah, I just made it. I have assigned this, and I have a water canal here in this direction. This is it's there, but it went. Its elevation you can see the assignments in the next layers. You can see the footprints of the river, like of the canal. You can see. So this canal, because those based on the elevation we can see. So this is the drainage canal, which means, so canal has its bottom surface, like elevation of the surface. So based on the elevation, it will go and sit in the layer. Suppose in the top elevation, the elevation is higher than the, the elevation of canal, it will go and sit in the next second or third layer. So that is why we couldn't see the river. I'm sorry, canal in the first river. Say go to first layer. So this is the river. Then I have seen the drainage. Then recharge. I need to assign a recharge. How much recharge is there? So so to assign a recharge, click single or polygon layer two actually. So yeah, so I have from in this study area, we have so many rivers, sea, and a drainage canal. So I assign the I have assigned the recharge for each thing, each location. So suppose I would say this is the I have assigned here property of one, like I would say new color, because already single blue color represents the recharge from other river. So it's a stop day, first day. It's so total days could be 365. Then I would say how much recharge. To calculate the recharge, again we have a formula. Uh, so using the formula, we need to calculate the recharge. Then assign the uh, then assign the if the recharge is same as one, you can say like no, it's mine is the same, my recharge is same. Or if you want new, you can say 365 days. It's how much is your recharge? Some 56. Okay, it's what I say. I don't want to save this, so I'm not going to save this. I think that's all. Yeah. So we are going to give evapotranspiration in this location. So after giving the evapotranspiration, it goes yeah, that's right. So evapotranspiration, we need to assign it. Yeah. So we need to assign like stop there, how much evapotranspiration is there. It's in the so evapotranspiration usually I took 10% of the rainfall. So the annual rainfall, I got the annual rainfall data from the government, and I try to measure I try to take 10% of it. That is how I made it. Yeah, it's not there. I didn't save that. So after assigning all these properties, we are almost done. We are about to run the model. So now just go to main menu, and here I didn't save any edited data because I just wanted to run my model safe without any errors. That is why. But usually when we are changing from section to section, properties to properties, we need to save it. If we don't save, no, because we need to track everywhere. It's kind of it's not very easy to keep on like tracking. We need to track. If we don't have any track, we don't know where the error is. So again, we have to start from the beginning. So we can say we can run the model in transient state or steady state. Let's say it, usually these options we will use to calibrate the model. In the I'll explain about the calibration and all so calibration. So usually if we have 10 years data, if we have 10 years data, so we will use 2 3 years data for the calibration. Calibration will tell us that yes, I recreated or I recreated the real conditions in the model. So, so what we'll do, we have 10 years data. We'll just use 2 years, 3 years data, and we'll recreate the model. After creating the model, we'll run the model. We'll get the output. By seeing the outputs, groundwater levels, we would say, yes, it is well calibrated. So it's kind of calibration and validation. Calibration, initially we will do in steady state condition. Then if it did well, then we will go to transient state. That is how these options will help us after steady state, because in real conditions, obviously there will be transient conditions, not steady state conditions in many cases. I don't say 100%, I cannot generalize it, but yeah, most of the cases we see transient state. We used to generalize, but so, right. So here we have mod flow, time steps, initial heads, and all multiplexer, multiplier. You know, these things will help us to run the model. Just click run. If you want zone budget, just click it. If you don't want mode path, click it. This is for solute transport model. Just ignore it. See, translate and run. That's all. I hope it will run. It's going on. This shows that our model is running. You can see here it's going a little slow. It's really going so fast. I don't know why. Say these are the solvers: PCG, SIP, SOP, WPF. Yeah, we got it. So you see here, this is the zone budget, in and out. This is what will. This is inflow and outflow. This is the flow terms. So inflow terms, again we got some storage. How much? So we changed the view, I guess. Yeah, yeah. So this red color represents the storage. Blue color represents the constant head. Then wells, then drains, then river leakage, evapotranspiration, the recharge. It's contribution. How much like its contribution. It should say inflow terms, and it's an outflow. These are inflow. How much water going from our study area. This is the outflow. That's all. We'll close it and we will open the output files. So coming to the output, I didn't run with the final file. I took some other file. That is why it is showing the dry cell. In my study area, output is not like this. Though there is dry dry cell, green color represents the dry cell, which means its surface is completely dry. Is what it shows. So I'm gonna turn off the dry cell layer. So we have some layers here. We can turn them off. If you want to see them, you can keep them. If you don't want to see them, just remove them. I want to see velocity vectors and other, say, net recharge. And if you want to see some, we have some other layers here. You'd say annotation, river boundary. If you want to see river boundary, if you want to know, we can change whatever we want to see. Now I remove that. So this is the output. Now I would like to see the graphs and to study the layer. I mean to study the compare the water level. I have 5 minutes more to. So yeah, so to see the RMS error and all, just see. This is the output. I just clicked all groups and apply. So when I applied it, I got RMS error as 13.84. It should be close to 10%. 10 as close, it means our model is more. Some of fields are almost away from it, which means they are not well calibrated, or or some other error. They might be calibrated. They might, those locations, might be, they're having more number of layers. So you can see most of the observation wells came very close to the line. So I would like to see the output. Suppose select a, and we got it. Select it. Select this. Just click it. This shows the actual scenario in the groundwater. So in day 14, groundwater level is here. In slowly it's coming down, 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 down. It's going like this. It means groundwater flow keep on going. This is completely away from all water bodies. It is away from the canal. It is away from the river. It is away from the sea in my study area. Let's see some other. I really don't know. I guess this one. If we see this, it initially groundwater head is there, and it's keep on going. This is little clear. From here, it started rising because in this day, like from this, like 1 year before, like almost six months before, water started flowing through. Like as I mentioned earlier, we have river A, Godavari River, river B, Krishna River. So Krishna River doesn't have enough water, so they constructed a lift irrigation project to uplift the water from river A to river B, river Godavari to river Krishna. So this village or this observation well is very close to the interlinked canal. So that is why up to certain days you can see the rise in groundwater level. That is how it works. If you want to see if you want to see 2-3 wells together, that is how it looks. So you can say this is the Unrajavaram, which is the location of another observation well. Nanuku, which is a location of another observation well. So we could say like we can see many observations. Whatever. These are names of the observation wells. Yeah, Vijeswaram, Veera was Sumaru. Yeah, you can see these are like that is how it works. So let me close this. I think I can't close this now. Yeah, close it. When I started screen recording, it's not allowing me to close or maximize or minimize the screen. So now I am done with this. Then go to head differential mode, like how much difference. You can see the contours. These are the velocity vectors. Let me explain them. This is the drawdown curves, contours, and all, like how water flows. I want to show you one thing. You mean you can see the head flux in the study area. Let's say, let me zoom it. Exaggeration. You can see the water flow. If you can see the arrow marks here, right? I hope you guys are able to see this. Yeah, this shows the water flow direction. This is like let me, yeah. So you can see this water is flowing away from the study area and it's going towards the sea, which means low elevation. It means obviously water will flow from high elevation to low elevation. That's what happening there. It is representing there. You can see when you zoom in this location, you can see the water flow. Water is flowing towards the sea and coming towards the river. This is the river location. It's coming towards the river. It's coming towards the river. Together going towards the sea. That's what it's doing there. Then we are going to see the budgeting. Some other outputs are there. I should. I don't have enough time, I guess. Zone budget. Go to zone budget. Zone output. You can see the numericals. how much water, how much river leakage, how much the graph which we saw there can be shown here. That's all. I think yeah, that's how it works. I think just a moment, like within 2 minutes, I'll try to show the layers. I forgot to show you that. So go to the properties, conductivity. How I assign the conductivity, I said, but I didn't show my show the layers, right? Let me show it. View column. View column will help us to see. So this is how our soil will be. But this blue shape is the top surface, soil surface. This is what it's showing. So if we want to see the layers from the side, this is how it looks. To close them, make it 500. Exaggeration. Zoom out, a little zoom out. We need to make it some 1500. You can see that. It's going to show that. This is because in some location it has the highest elevation point in my study area. That is how it looks. And let me view through the row. Let me view through column. So this shows. So this is the column view. This is the row view. This direction. I'm seeing this row, column. That is how, like, we are seeing in all the way we can see. So if we zoom it here, so we can see the top layer, blue, 3, 4, 5, 6, 7, 8, 9 layers. In one location we have 10th layer. That is how I created the model. This is the sand dunes. This is a little complicated area, so we got too many areas, which is kind of headache. So we are going to give conductivity of each location. I'll try to show you that. Let's click here. So if we see here, we'd say property number, layer number is layer number is 6, I guess. Yeah, it's kx, k minimum, ky, kz. Z is like almost 10% of, yeah, 10%, I guess. Yeah, 10% of the kx and y. SS, storage, specific storage, specific yield, storage, effective porosity, total porosity, each layer I gave. Yeah, that's all. So we have this facility. I forgot to show you. So that's all for that's all about our MODFLOW. I hope I try my level best to explain you. Actually, I need a little more time to explain in detail. If you are aware of groundwater, aquifer properties and all, at least I wish you guys got some overview on Visual MODFLOW. Thanks a lot, and thank you, Dr. D. Thanks for giving me thanks a lot. Thank you for giving me this opportunity, and stay safe. We will meet soon. Thank you.